Hello students, welcome to the class. So in the previous class, we had discussed something regarding ionization energy. So it is the minimum amount of energy required to remove an electron from the isolated gaseous atom in its ground state. Whatever energy is required to remove the electron from the neutral gaseous atom, suppose I have a neutral gaseous atom. You cannot remove the electron from solid atom. Okay, you have to convert it to gaseous vapors. The atom, when you remove an electron, it forms a cation when electron is being removed. So this electron cannot be removed as just by saying. Yes, I cannot say electron come out, then it will come out. No. Why? Because the electron is held by the nucleus, or you can say it is held by the nuclear charge. There is attraction between the electrons and the nucleus. Therefore, I need to submit a little amount of energy, minimum amount of energy, and that is called ionization energy. The energy required to remove the first electron from the outermost shell is called first ionization energy, denoted as IE1, or it is also denoted as delta H1. Yes, here we say delta Hi, ionization energy. Then the subsequent removal of electrons, removal of second electron from the atom is defined, is said as second ionization energy, or delta IH2. Yes, you cannot remove the electrons at a stretch. You have to remove them in a successive manner, that is one after the other, successive manner. I cannot say I'll remove the electrons simultaneously. No. In one case I'm removing one electron, this side I'll remove second electron. No, they have to be removed in a successive manner, one after the other. Once the first electron is lost, it will form a unipositive cation. Removing the electron from the unipositive cation becomes difficult. Yes, remove the electron from the unipositive cation becomes difficult, because when an electron is lost from the atom, when an electron is lost from neutral atom, what will happen? From the neutral atom, number of electrons decrease. Yes, as number of electrons decreases, nuclear charge, nuclear attraction on the remaining electrons increases. Nuclear attraction on remaining electrons, increases. Yes or no? Remaining electrons increases. So when this nuclear attraction on the remaining electrons increases, removing the next electron from the same positive cation becomes difficult. Therefore, we say when there are successive ionization enthalpies, if there are four successive ionization enthalpies, the fourth ionization enthalpy is more than the third ionization enthalpy, which is more than the second ionization enthalpy, which is more than the first ionization enthalpy. Yes, and how these ionization enthalpies come? From the metal atom, you apply first ionization energy, you'll get unipositive cation, one electron comes out. You take unipositive cation, apply ionization energy, then you will get bipositive cation, one electron comes out. Bipositive cation, apply ionization energy, third ionization energy, you'll get a tripositive cation, one electron comes out. Similarly, tripositive cation, apply fourth ionization energy, then you will get pentapositive or polypositive cation. Yes, one electron comes out. Yes, so these are called as, what they are called as, successive ionization enthalpies. So to conclude all of this, the electrons, I can say, when we consider the electrons in an atom, correct? So when I consider, so if I say this is my nucleus, with positive charge, and I know electrons are revolving around the nucleus, right? They are revolving around the nucleus. So the electrons in an atom, they are attracted by the nucleus. When electron is to be removed, then work is done against this nuclear attraction. Work has to be done against the nuclear attraction. What does that mean? In other words, energy is required to remove the electron from an atom. To understand the details of the chemical behavior of an element, we must have indication of energy with which an atom binds its electrons. This is obtained by the measurement of ionization potential, IP, or ionization energy, or you can say ionization enthalpy. It may be defined as the minimum energy required to remove an electron from the outermost shell, valence shell of an isolated gaseous atom in its ground state. in its ground state. So first we consider ground state. If it is ionization potential, it is expressed in electron volts or it is expressed in kilocalories per gram atom. In an atom, the energy required to remove the first electron from the gaseous atom is called first ionization energy. The energy required to remove one electron from a unipositive ion to form a bipositive ion is called second ionization energy. Second ionization energy is always higher than first ionization energy. The reason is that what happens in unipositive cation? In unipositive ion, left after the removal of one electron from the atom, the electrons number decreases. Therefore, we say the electrons are more firmly bound to the nucleus than in the atom. Hence, more energy is needed to remove the second electron. Yes, so this is about the successive ionization energies. Now, I have a question here. Suppose I consider elements of any element of group 1, any element of group 2, and any element of group 2 and any element of group 13. Yes, okay, let me consider sodium here, atomic number 11. In this case, I will consider magnesium, atomic number 12, and here I will consider aluminium, atomic number 13. Okay, when I say sodium atomic number 11, it is 1s2, 2s2, 2p6, 3s1, right? Magnesium, 1s2, 2s2, 2p6, 3s2. Aluminium, 1s2, 2s2, 2p6, 3s2, 3p1. Correct? So if you look here, how do I denote the outermost number of shells? This is first shell, second shell, third shell. First shell, second shell, third shell. First shell, second shell, and third shell. Right? Okay, fine. Now, if you see here, sodium atom, it is a neutral gaseous atom. If I submit first ionization energy, what does that mean? I'm going to remove the first electron that from the outermost shell. So this electron gets lost. So it will form Na plus one electron is lost. So it forms a unipositive ion. Now, when it forms a unipositive ion, look at the configuration. Here I can write it as this. I will write it as 2 electrons in the first shell. Second shell, how many electrons? 8 electrons. Third shell is 1 electron. When this 1 electron from the outermost shell is lost, it will form configuration 2, 8. And always remember, noble gases, they have 8 electrons in their outermost shell. Because of this 8 electrons in their outermost shell, they account for high stability. Except noble gases, none of the elements have 8 electrons in their outermost shell. Therefore, we say all the elements except noble gases, they tend to acquire 8 electrons. When any element, any atom acquires 8 electrons in the outermost shell, it becomes extremely stable, students. It becomes extremely stable. Okay, please do remember this point. And we call it as octet configuration. Octet configuration is the most stable configuration. Now come back to this. So when you apply first ionization energy to sodium, or you can say any element of a group 1, when I apply first ionization energy, what happens? It will lose the outermost electron, and configuration of any element of group 1 will have 2, 8 configuration. That means, or I can say 2, 8. Outermost shell will have 8 electrons. And you know that if there are 8 electrons in the outermost shell, it accounts for extra stability. Now for this Na plus ion, if I apply the ionization energy, do you say the ionization energy will be more? Quite obvious. We know this rule, right? We know this rule already. What we know? The second ionization energy is more than first ionization energy. But in this case, if you are observing, I am going to apply the energy in order to remove the electron from most stable configuration. Therefore, can I say I will have to put more and more amount of energy in order to remove the electron and to make it Na plus 2, which is highly impossible actually. Yes, which is highly impossible, because when sodium loses one electron, it becomes heavily stable. That is, it occupies 8 electrons in its outermost shell. So if I want to remove from that highly stable configuration one electron, I need to put more and more amount of energy. Therefore, here I just cannot say that the second ionization energy is more than first. No, no. The second ionization energy is very much more than the first ionization energy. The second ionization energy is very much more than the first ionization energy. Understanding? Getting my point? Is very much more than the first ionization energy in case of not only sodium, in case of all the elements in of group 1, in case of all the elements of group 1. Yes, so if you want here, I can tell you the first ionization enthalpy of sodium is 496 kilojoules per mole. That means 496 kilojoules per to remove an electron from 1 mole of sodium atoms, I need so much ionization energy. But if you look at the second ionization energy of sodium, that means to remove the second electron from sodium, which is high, has got high stability, it is 4563 kilojoules per mole. Just imagine. Here it is 496, around 500, and here it is 4000. So can I say it is very, very, very much more. So this high amount of energy, it shows that the second electron cannot be lost by, so what it shows? It shows that for any element of group 1, it can lose only one electron and attain stability. Any element of group 1 can lose only one electron and attains stability. Attains stability. Is that clear? Therefore, we say group 1 elements, they form unipositive ions with valency equal to +1. They form unipositive ions. Is this point clear? Okay. Coming to group 2 elements, magnesium. Now, for magnesium, I will apply the first ionization energy and one electron from this is lost. So it becomes Mg plus 1 electron comes out. Here configuration is 2, this is 8 and outermost shell has 2. So when magnesium loses 1 electron, it becomes 2, 8, 1. Okay. Now to this Mg plus ion, unipositive ion, which has configuration 2, 8, 1, I will apply the second ionization energy to remove one more electron and it becomes Mg plus 2. Mg plus 2 will have what configuration? 2 and 8. It will have configuration 2 and 8. Yes, now you can observe, unlike sodium, magnesium can, by losing its 2 electrons or group 2 elements, when they lose 2 electrons, they attain 8 electrons in valence shell. That accounts for what? It accounts for stability. So if I want to remove one more electron from Mg plus 2 ion, which has attained octet configuration, is it easy? Is it possible? It is not possible. Or if it has to be possible, you need what? You need what? You need extremely high amount of energy. In general, we say, what we say in general? We say that the third ionization energy is more than second ionization energy, which is more than first ionization energy. But in case of group 2 elements, the third ionization energy is extremely more. The third ionization energy is extremely more. Yes, it is extremely more. Why it is extremely more? Because in case of group 2 elements, after losing 2 electrons, it will attain the stability. I can show you here. Here, the first ionization energy of magnesium is around 737 kilojoules per mole. The second ionization energy of magnesium is around 1450 kilojoules per mole. And the third ionization energy of magnesium is, see here, 7733 kilojoules per mole. Now see, what questions will be given is they will give the ionization energies. You need to predict what type of ion can be formed. So if there is a large gap, if there is gap, okay, the gap is accepted because we all already know the higher ionization enthalpies are more than the lower. So this is accepted. But look here, this is 1450 and the third ionization energy is 7733. Therefore, I say the third ionization energy is heavily more than the second ionization energy. That means the given element can form only bipositive cation. It can form only bipositive cation. Therefore, group 2 elements, I say, they can have the tendency to lose only 2 electrons. All the elements of group 2, whether it is beryllium, magnesium, calcium, barium, strontium, they have the tendency to lose 2 electrons only, because once they lose 2 electrons, they attain high stability. They attain high stability because they will have 8 electrons in their outermost shell. Yes, or you can speak on the basis of ionization energies. Looking at the ionization energy values only, you can say. So if you see here, first ionization energy is so much, second is so much, therefore we say it can form only unipositive ion. Second ionization energy is so much, third is so much. So we can say it will stop here only. It will form a bipositive cation. Is that clear? Yes. So it will lose only 2 electrons and attain the stability. Therefore, all the elements of group 2, they have the valency plus 2. They exhibit the valency of plus 2. Okay. So this is about the ionization energies of group 2 elements. Okay. Next, moving to the next one, let us consider elements of group 17. Elements of group 17. Okay. Okay. I'm sorry, elements of group 13. Okay, fine. So aluminium. It is aluminium. Fine. Atomic number of aluminium is 13. So I can write aluminium. When you apply the first ionization energy, this can be represented as 2, 8 and 3. So aluminium will lose 1 electron and it forms aluminium plus ion. Its configuration comes to 282. Al plus unipositive ion, apply the second ionization energy, it will form Al plus 2 with the loss of 1 electron, whose configuration will be 281. Al plus 2, apply the third ionization energy, it will form Al plus 3 ion with configuration 28 by loss of 1 electron. Now, if I take Al plus 3 and apply the fourth ionization energy, can I say the electrons will be lost easily? Yes, the electrons will be lost easily just by applying more ionization energy than the third one. Can I just say, can I conclude saying just by applying ionization energy, fourth ionization energy is little more than the third ionization energy, the electron will be lost? No. Yes, this rule is followed. But if you look in case of aluminium, after losing 3 electrons, aluminium has got a stable configuration of 8 electrons in its outermost shell. 8 electrons in its outermost shell. Understanding? Yes, 8 electrons in the outermost shell. Therefore, so it is octet configuration, most stable configuration, most stable configuration. Therefore, we say aluminium can lose maximum of 3 electrons only. It can lose maximum of 3 electrons. If you want to remove the fourth electron from the stable configuration of 8, then you need to apply very high amount of energy. Therefore, we say the fourth ionization energy of aluminium is very high. So if I give you this order, what does this mean? If I ask you, that means after removing one electron, I need more energy to remove second. After removing second electron, I need more energy to remove third. But after removal of three electrons, I need very large amount of energy. Means what? It means After losing 3 electrons, the particular atom has attained stability. Therefore, we can say it exhibits a valency of +3. It can lose only 3 electrons. Yes, I can show you the ionization energies also. The first ionization energy of aluminium is 577 kilojoules. The second ionization energy of aluminium is 1816. The third ionization energy of aluminium is 2881 kilojoules per mole. The fourth ionization energy of aluminium is 11,600 kilojoules. See the difference. 577, 1816, 2881. Fourth is 11,600 kilojoules. Yes, very, very large amount of energy. That means aluminium or any element of group 13, they have the capability to lose 3 electrons, because after losing 3 electrons, they attain stability. They attain stability with the electronic configuration of 8 electrons in the outermost shell, which we call it as octet. So this is how ionization energies vary. Ionization energies vary in the different groups. Based upon the ionization energies only, we can say the elements of a particular group, they show what type of oxidation state. So group 1 exhibits +1 oxidation state because its second ionization energy is extremely high. Group 2 elements exhibit the +2 oxidation state because its third ionization energy is extremely high. Group 13 elements, they exhibit +3 oxidation state because their fourth ionization energy is extremely high. Fourth ionization energy is extremely high. So even you can take different examples. You can mention different examples to quote this explanation. Yes, so this is about the ionization energy enthalpy of various elements. Okay, so here you can see I have taken the same example. See, fourth, if you see, it is 11,600. So aluminium can form a tri-positive cation only. Yes, factors governing ionization enthalpy or energy. Normally, when the ionization energy is high, what does that mean? If we say for an atom the ionization energy is very high, it means it will be more difficult to remove an atom. Yes, there are several factors that govern the attractive forces. If nucleus is positively charged, then electrons are strongly attracted to it. If an electron lies near or close to the nucleus, then the attraction will be greater than one when the electron is further away. If there are more electrons between the outer level and the nuclear, attraction is less because inner electrons there will be repulsion. When there are two electrons in same orbital, they experience some form of repulsion. Now this creates disturbances in the attraction of the nucleus. In essence, ionization energy will be less in paired electrons as they can be removed easily. Yes, so these are some of the factors. Now how to understand these factors? Factors governing the ionization energy. The first factor is size of the atom. This is the first factor. How to explain the size of the atom? Okay, let me consider this atom and let me consider this atom. Okay, here is the nucleus. Fine. Okay, in this case, here is the nucleus. Done. Fine. Okay. So if the atomic size is large and if the atomic size is small, what will happen? And you imagine this is the outermost shell here, this is the outermost shell here. So this is nucleus, this is nucleus. With the increase in the atomic size, what happens? With the increase in the atomic size, the distance of the outermost electron, the distance of the outermost electron from the nucleus increases. As atomic size increases, the distance of valence electron from nucleus, it also increases. As the distance of the electron, as the distance of valence electron increases, nuclear attraction, what happens to the nuclear attraction? It decreases. Nuclear attraction decreases. Therefore, just if I put very less ionization energy also, electron will be lost. Electron will be removed. Yes. But in case if the atomic size is small, the distance from the distance of the outermost electron, the distance of valence electron from nucleus is what? It is less. So when the distance is less, what happens? The distance is less. The nuclear attraction is, what happens? Nuclear attraction will be more. Nuclear attraction will be more. Nuclear attraction on that electron will be more. It will be more. So when nuclear attraction is more, you need to put more ionization energy, then the electron will be removed. Yes or no? So size of the atom is the first factor. As the size of the atom increases, the distance of the outermost electron from the nucleus increases. As the distance of the outermost electron increases, the nuclear attraction decreases. So only if you apply very less amount of ionization energy also, minimum of the minimum ionization energy, electron gets removed. But in case if the atomic size is small, the distance of the valence electron from the nucleus is very less, due to which the nuclear attraction is very strong. Nuclear attraction is very strong. So you need to put, to remove the electron from the vicinity of the nucleus, I need to put more amount of ionization energy. Then only the electron will be removed. So this is the first case. This is the first case. Okay. What is the second factor which affects the ionization energy? The second factor. The second factor which affects the ionization energy is charge on the nucleus. So what does this mean? With the increase in the nuclear charge, as the charge on the nucleus increases, there is increase in the force of attraction on the nucleus. So let me say I have unipositive cation plus 2 cation. This is unipositive and this is bipositive. So what is having? What is happening? The charge on the cation is increasing. So as the charge on the cation is increasing means what? Nuclear attraction is increasing. The electrons are held more strongly. Yes. So with the increase in the nuclear charge, there is increase in the force of attraction of the nucleus on electrons. So force of attraction, nuclear force of attraction increases on electrons. Yes. So when nuclear force of attraction on the electron increases, it makes the removal of electrons more difficult. So removal of electrons becomes difficult. It becomes difficult. Thus, an increase in nuclear charge increases. So as the size of the atom increases, ionization energy decreases. But as the charge on the nucleus increases, ionization energy also increases. Yes, so only we say for unipositive cation, what ionization energy is required? Bipositive, to make it bipositive, more ionization energy is required. So only we say E2, yeah, ionization energy, second ionization energy is more than first ionization energy. Yes. Next, what is the third condition? The third condition is shielding or screening effect. We know what is shielding or screening effect, right? Shielding or screening effect. The valence electron in the multi-electron atom. So if this is multi-electron atom, okay, so this is, let me say, nucleus. So these are the shells, first shell, second shell, third shell. So there are, let me say, electrons here. Okay, so here there are electrons revolving. So this is the outermost shell, let me say. The valence electron in this multi-electron system, they are pulled by the nucleus. Yes, there is attraction by the nucleus. On the same time, there is repulsion by the inner electrons, but they are repelled by the electrons present in the inner shells. The valence electrons, therefore, do not experience the total pull of the nucleus. There is attraction. So, attraction is there. But along with attraction, there is repulsion by the inner electrons. Therefore, we say the valence electron do not experience the total pull from the nucleus. Instead, the total attraction of the nucleus is reduced by the electrons in the inner shells. This effect of reducing the force of attraction on the valence shell is called what? Shielding or screening effect. And this effect is exhibited maximum by S2 and P6 shell, which is said to be most stable shell. This is most stable shell because it is having 8 electrons. See, 6 plus 2 is 8. Therefore, ionization energy is much less than the others. This ionization energy is very high. When you compare it for others, it is very less. Let me take an example. Potassium is 19, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Yes. Copper 29, 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s1. Yes or no? 3d10, 4s1. So ionization energies, if you see, yes, of K is much less than copper because here there are more number of inner electrons. They will shield this valence electron. So ionization energy of this is very less. So this is due to large screening effect of these inner shell electrons. Inner shell electrons. Understood? So shielding or screening effect is one of the example. Next reason. Yes, it depends on, the next point is, it depends on the type of electrons involved. One more reason. It depends upon the, please do remember all these points. Questions appear on these basis only, factors only. Type of electrons involved. Ionization energy also depends upon the type of electrons involved. Type of electrons means, is it S electron? Is it P electron? Is it D electron? Is it F electron? Which are able to remove. See, S electrons, they are closer to the nucleus. So when they are closer to the nucleus, they are more tightly held as compared to PDF, correct? As compared to PDF. Therefore, we say ionization energy. We say ionization energy, it decreases in the order. It decreases in the order. In what order? So highest ionization energy is required to remove S electrons, then P electrons, then D electrons, and then electrons in the F orbital. So this is another reason. Yes, and there is one more last reason. We call this reason as penetrating effect. Since S electrons are very close to the nucleus, penetration, they are very penetrated to the nucleus. So attraction is more. So I need to put more amount of energy to remove S electrons. So if I have S and P electrons, which electrons I have to put more energy? It is for S electrons. So ionization energy required to remove S electrons is more than the ionization energy required to remove P electrons, which is more than the ionization energy required to remove D electrons, which is more than the ionization energy required to remove F electrons. And the last one is completely filled or half filled subshells. Yes, we know that extra stability accounts for completely filled or half filled subshells. So if you have completely filled or half filled subshells, what happens? The ionization energy will be very more. The best example to quote here is, take the atomic numbers of elements sodium and oxygen. Yes, how they are present in the periodic table. Sodium is here, oxygen is here. So if you see atomic size, yes, as atomic size increases, the ionization energy decreases. So if I see across the period, atomic size, what happens? Atomic size decreases. So if this is the atomic size of sodium, sorry, nitrogen, I'm very sorry, then this will be the atomic size of oxygen. Correct? Understanding. So as you move across the period, atomic size decreases. Yes or no? Atomic size decreases. So if this is atomic size of nitrogen, this is atomic size of oxygen. So where I need more energy to remove the electron, I should need ionization energy of oxygen should be more than the ionization energy of nitrogen. Let us see. But this is expected. This is what? Expected. Okay. But actually, if you see the ionization energy of nitrogen is more than the ionization energy of oxygen. This is what? This is actual. Actually, if you see, this is correct. Now let us see why. Okay, let us see why. According to our first factor, as size increases, ionization energy decreases. So as size increases, ionization energy decreases. So ionization energy of nitrogen should be less and ionization energy of oxygen should be more. But here, ionization of energy of nitrogen is more than ionization energy of oxygen. Let us see the reason. Configuration: 1s2, 2s2, 2p4. I'm sorry, 2p3. Correct? Write the orbital diagram. Similarly, for oxygen, configuration is 1s2, 2s2, 2p4. And let us write the orbital diagram. Yes, looking at the configuration, immediately we don't come to the conclusion. If you look at the orbital diagram, you'll understand. 1s2. So how many electrons? 2 electrons. Spin up, spin down. 1s2, spin up, spin down. 1s2p3. 2s2, 2p3. Hund's rule of maximum multiplicity. Pairing of the orbitals does not take place. You cannot do it like this until each orbital is half occupied. So it is 2p3. Oxygen 1s2, 2s2, 2p4. Spin up, spin up, spin up, and then spin down. Yes. Now observe the configurations of nitrogen and also observe the orbital diagram of oxygen. Yes, if you observe it carefully, you will come to the conclusion that the outermost orbital of nitrogen is having half filled configuration. Half filled configuration, whereas this is not having any half filled configuration. And we know that half filled configuration due to two reasons. What are the two reasons? The two reasons are, one is symmetry and other one is exchange energy. So because of these two reasons, half-filled configurations are more stable and even completely filled configurations are more stable. So since the nitrogen has got half-filled configuration, it becomes more stable. Therefore, if I want to remove electron from nitrogen, I will have to put more energy to remove the electron from nitrogen as compared to removing the electron from oxygen. Therefore, we say what? We say the ionization energy of nitrogen is much more than the ionization energy of oxygen, though atomic size of nitrogen is more than atomic size of oxygen. Understanding? So it is because of the fifth factor, because of the half filled electronic configuration, which accounts for more stability, the ionization energy becomes more, and it does not obey the first, the first factor. Yes, so these are the factors which affect the ionization energies. So completely filled or half filled subshells. What does it say? According to Hund's rule of maximum multiplicity, completely filled or half filled orbitals are more stable. Therefore, it is comparatively difficult to remove the electrons from these shells. Comparatively difficult to remove the electrons from these shells. Yes. Example, even you can take example of beryllium and boron. Beryllium has configuration what? 2s2. Boron has 2s2 2p1. Correct? So ionization energy of beryllium is more than boron because beryllium has 2s2 configuration, which in which the outermost shell is fully filled. So 2s2, outermost shell is fully filled. Yes. Similarly with nitrogen and oxygen. So if you see in electron volts, the nitrogen ionization energy is 14.6 electron volts, whereas for oxygen it is 13.6 electron volts. Yes, because nitrogen has outermost shell configuration as P3, which is symmetrical, which is half filled. P subshell is half filled and it is more stable. It is more stable. Yes. Similarly, ionization energy of magnesium is more than that of aluminium, and ionization energy of phosphorus, it is more than that of silicon. Similarly, all the elements of the ionization energies of group nitrogen belongs to which group? 15 are more than the ionization energies of group 16. Yes, I can say it like this. The ionization energies of group 15 are more than the ionization energies of group 16, though the atomic size of group 15 are more than atomic size of group 16. The reason is because completely filled or half filled subshells are more stable. Removing the electrons from the completely filled or half filled subshells becomes more and more difficult. It becomes more and more difficult. Is that clear? Okay. So if you see ionization energies of second period elements, I can show you all first ionization energies. How do they vary? Lithium, which is less. Boron comes first rather than beryllium. Then comes beryllium. Then carbon. Expected is nitrogen, but oxygen comes first. Then nitrogen. Then fluorine. And last comes neon. Noble gases have got very high ionization energies. Yes. Similarly, if you see group third period elements, ionization energy of third period elements, first ionization energy, sodium, before magnesium comes aluminium, then comes magnesium. Before silicon, before sulfur comes silicon, sulfur, phosphorus, chlorine, and then argon. Yes. So ionization, first ionization elements with very high values. The ionization, first ionization elements of elements, first ionization energy of the elements with very high values. If you want to know which are those high values, then it is for chlorine is highest, then comes hydrogen, oxygen, Kr, krypton, nitrogen, argon, fluorine, then comes neon, and then comes helium. This is the first ionization energies of the elements with very high values. Yes. So with this ionization energies, what information do we get? If the ionization energy is very low, lower the ionization energy means what? Lower the ionization energy, more easily electron is lost. More easily electron is lost. Loss of electrons is called its reducing property. So there I can say, so more is its reducing power. Therefore, we say metals are reducing agents. So more will be its reducing power and reactivity. And also reactivity. This is the importance of ionization energy. Lower the ionization energy, more easily the electron is lost. So more will be its reducing power. Yes. It also gives us the rough idea about the basic character. basic character of elements. Yes. Third point, if you consider the ionization energy of an element, of an atom, and there is one more trend, that is electron gain enthalpy. Electron gain enthalpy. If you just verify both of them of different atom, then you can explain the nature of bond formed between the atom. The nature of bond formed between the two atoms. If you know ionization energy of one atom and electron gain enthalpy of the other. Next, the ionization energies, they tell us information regarding number of valence electrons. Based on the ionization energy, we can say how many valence electrons are there in an atom. How many valence electrons? If there is abnormally high ionization energy, it means what? It indicates that electron removed is other than the valence electron. If there is abnormal high energy, then the electron to be removed is other than valence electron. Valence electron. So you can predict how many valence electrons. You can see how many electrons, valence electrons are there in an atom depending upon looking at the ionization energy. So if there is abnormally high ionization energy, then it means what? It means that you are removing the electron other than valence electrons. Yes, other than valence electrons. Let me give you so this is the significance. What it is? It is the significance of ionization energies. Significance of ionization energies. First one, lower the ionization energy, more easily the electron is lost. Tendency of losing the electrons. It is reducing power. So more is its reducing power and therefore reactivity. That's the reason we say metals are reducing agents. They can be used as reducing agents. Yes. Okay. They have the reducing power, reduction power. And it tells us about the basic character of the elements. Rough estimate about the basic character it gives. Ionization energy gives. Ionization energy of an atom, and if you consider electron gain enthalpy of other atom, then when they are combining, during the combination, what type of bond, the nature of bond formed can be told. If you know the ionization energy of one atom, and that means if there are two atoms A and B, one atom ionization energy, other atom electron gain enthalpy, if you know, they are denoted like this, delta IH, delta EGH. If you know these two, you can predict when they are combining what is the nature of the bond formed. Even it gives information about the number of valence electrons in an atom. If there is abnormally high ionization energy, then whatever electron you are removing, it is other than the valence electrons. It is other than the valence electrons. So this is the significance of ionization energies. A small example to quote this. See, ionization, first ionization energy, second ionization energy, third ionization energy values are 5.39, let me say this, 75.62, and this is 122.42 electron volt. Yes, so where there is a sudden jump. So you can see here, if these are the ionization energies of a certain atom say M, since the values show sudden jump, it indicates what? There is sudden jump, right? It indicates what? It indicates that number of valence here from 5, there is sudden jump to 75. So since the value shows sudden jump, it indicates that the number of valence electrons in the atom is how much? It is only 1. It is only 1. Yes. So these values doesn't make any difference. When metal atom is there, it is losing electron, and this is the first ionization energy, 5.32. From the unipositive cation, it is requiring so much electron volts of energy to become dipositive. That means what? That means once it has lost the electron, it has attained stability. It has attained stability. That means the outermost shell or the valence shell has got only one electron. So there is one electron in the valence shell. Later, once you remove one more electron from that stable shell, it becomes 7. Again, it becomes unstable. So there is no much difference on it goes on increasing. That's it. Yes. Second example. Okay. Let us consider second example. The ionization energies, the first, second, and third ionization energies of certain element are 9.32 electron volt, 18.21 electron volt, and 153.85 electron volt. Okay, that means what? It means that there is a metal, apply first ionization energy, it forms a cation. So that ionization energy is 9.32. From the cation, you apply second ionization energy, it forms dipositive ion, and the ionization energy required is 18.21. From the dipositive ion, you apply certain ionization energy, say it is given 153.85, you will get a tripositive ion. Yes. So where there is a sudden jump, there is sudden jump in the third ionization energy. So sudden jump in the third ionization energy, it indicates what? The sudden jump in the third ionization indicates that the electron is getting removed is not the valence electron. It is some other electron from the stable configuration. That means losing two electrons, the metal has attained stable configuration. And here there is a large ionization energy required. That means you are removing the electron from the inner core. You are removing electron from the inner core. Therefore, the given metal atom contains how many electrons? It contains two valence electrons. Or you can say it exhibits the valency of +2 only. It exhibits the valency of +2 only. Yes. So this is a small example on ionization energy. Yes. Okay. So we have read this. When there are two electrons in the same orbital, yes, we have read this also. Variation of ionization enthalpies in the periodic table. This variation of the ionization enthalpies we will take up in the next class. I'll just tell you, please do remember, across the period, what happens to the atomic size? Yes, across the period, atomic size decreases. Correct? And down the group, atomic size increases. Since atomic size, there are certain exceptions, okay? So since atomic size is the factor which governs what? Which governs the ionization energy across the period, what should happen to the ionization energy? Atomic size is decreasing. You can understand this very well here. Can you see this? Across the period. Forget about the first period. We'll see from the second period. Because first period, hydrogen has to be placed separately. Helium, okay, we'll consider from the second. Second period, third, fourth, fifth, sixth, and there is seventh down. Francium element is there. Okay. Across the period, atomic size is decreasing. Can you see here? It is decreasing. So as the atomic size decreases, the nuclear attraction on valence electron increases. The nuclear attraction on the valence electron increases. When the nuclear attraction on the valence electron increases, we are going to discuss only till here. The nuclear attraction on the valence electron increases. When the nuclear attraction on the valence electron increases, what happens? We need to put more energy to remove the electron. So here I need less ionization energy. But when you go from left to right in the periodic table, the ionization energy increases. Yes. Top to bottom, if you see what happens, there is increase in the atomic size. Atomic size is increasing. So when atomic size increases, what will happen? When atomic size increases, the valence electron, there is large distance between the nucleus and the valence electron. As the distance from the nucleus, as the distance of the valence electron from the nucleus increases, nuclear attraction decreases. So as nuclear attraction decreases, you need to apply less energy to remove this electron. So as atomic size increases down the group, the ionization energy down the group, the ionization energy down the group decreases. Yes, very less amount of energy you need to put to remove the electron from the outermost shell. From the outermost shell. Yes, is that right? So this is a slight explanation, introduction regarding the variation of ionization enthalpies in the periodic table. So along the period, ionization enthalpies are expected to increase in moving across from left to right because the nuclear charge increases as the atomic size decreases. In a group, the ionization enthalpies of the elements decrease on moving from top to bottom in any group. Yes, why? Why it decreases? Because there is increase in the number of main energy shells. That means atomic size is increasing in moving from one element to another down the group. So when the atomic size is increasing, when the atomic size is increasing, yes, there is also increase in the magnitude of screening effect. So inner core electrons will show repulsion on the outermost electron. So atomic size is increasing, screening effect is also increasing. Therefore, I need to put very less ionization energy. What happens if you put very less ionization energy? Also electron gets lost, removed. So there is also increase in the magnitude of screening effect or shielding effect due to gradual increase in the number of inner electrons. So you can see here the ionization energy: lithium, sodium, potassium, rubidium, cesium 500. As we move down the group, the ionization energy is decreasing. 500 kilojoules per mole, 496, 420, 402. Cesium it is 376 kilojoules. So as we move down the group, ionization energy is decreasing. But when you move across the period, lithium, beryllium, you can see this is second ionization energy. Observe this, first ionization energy. Lithium first ionization energy is 500. Beryllium first ionization energy is 899. So as you move across the period, the ionization energy increases. So beryllium 899, magnesium again as you move down the group it decreases. This is first ionization energy, and for group 2 elements this is the second ionization energy. As soon as it they so because group 2 elements form bi-positive ions, therefore I have shown you all the second ionization energy is also in this. Yes, so with this we will just stop about discussing about the ionization energies. In our next video we'll stop this class here for now. In our next video we'll discuss about the next periodic trends. Hope you have got cleared with the ionization energies, the factors governing the ionization energies, and even what is the importance of ionization energy, why we should know. Please do follow all these concepts, students, because the next chapter is a very big chapter, chemical bonding. All these factors are required in that topic to understand various important concepts there. Okay, so please try to recall all the things what we have discussed, especially in the ionization energies, successive ionization energies, first, second, third, fourth, why there is a huge jump, what it indicates, all those things should be practiced very well. In the next video, we'll be discussing the next part of the topic. For now, thank you.